In the previous video, we talked about the epsilon n definition of the limit. So we say a sequence an converges to a as n goes to infinity when this kind of thing happens. The distance between an and a gets arbitrarily small as n gets sufficiently large. And arbitrarily small is related to less than epsilon, which is arbitrarily selected. And sufficiently large means n is larger than a certain capital N, which it is a certain natural number, just sufficiently selected. Something exists like that. And analogy, the analogous definition for limit of function goes kind of like this. We say f of x converges to L as x goes to infinity, as something like this happens. The distance between f of x and L gets arbitrarily small as x gets sufficiently large. So actually, what do I have here? Excuse me, this should have been f of x minus L gets arbitrarily small, so that is smaller than epsilon bound, which is selected arbitrarily. If x gets sufficiently large, and then that means x is greater than a certain bound m, which is a just positive real number. A certain positive real number exists such that blah blah blah. As a matter of fact, I should have completed the color coding. When that happens, we say we have convergence. And here's a visualization. We talked about these kind of things. When epsilon is relatively large, then there's no reason to select really large m value for function or capital N for sequence. If epsilon got smaller, then it becomes a bit more necessary to take a little bit larger m value for function or capital N value for sequence. Now, as you can see in the third picture, this red one, if epsilon gets really small, then it becomes really necessary to get rather big m value or capital N value. So there goes the visualization and then the definition. Now let's talk about some theorems. And I don't know whether we can actually prove any of those here, but let's try at least a little. The first one, the uniqueness of limit, is simply enough. I think we can handle it. Now, it goes like this. If an converges to a, and an converges to a hat, then a and a hat must be the same, which means the limit is unique. No sequence can converge to two different values. If it gets very, very close to two different values, then it's not a convergence, it's an oscillation. And the definition kind of goes like this. An minus a has to be arbitrarily small, isn't it? So we select arbitrarily epsilon, and it has to be less than that. But then again, it's arbitrary, so we can start from epsilon over 2, because epsilon is arbitrary, so we begin with twice the number that we want and then got into epsilon over 2. We can always do that. Likewise, an minus a hat is less than epsilon over 2. Again, epsilon over 2 is arbitrary. So what do we have? We use something called triangle inequality. a minus a hat can be rewritten as a minus an plus a hat. Basically, I just inserted an and subtracted and added so that I didn't change anything. And here comes a critical step, the triangle inequality. We just separate the addition into the addition of absolute values. Here we may have some cancellation. Here we have just sum of two positive or non-negative real numbers, so there's no cancellation there. So this expression here should be bigger than or equal to that expression. Consequently, what do we have? This one is less than half of epsilon, as we said over there, and that one is less than half of epsilon, as we said over there. So what we have, adding up together, a minus a hat is less than epsilon, which means this fixed real number is less than every positive real number. How can it be? I mean, if it is a positive number, if this highlighted number is positive number, then it cannot be less than every positive real number. I mean, what if I select half of this this highlighted number? We're gonna have that's contradiction right away. Well, if that's too difficult to understand, think of it this way. Excuse me. A real number that is less than every positive real number is either negative or zero. And of course, this is absolute value cannot be negative, so it has to have zero. So when do we have zero? Absolute value is zero, so a minus a hat is zero. We must have equality. Well, in short, the limit is unique, so we can use limit notation and then we can do all kind of things with limit. If it is not unique, then you can't really do anything about it. It's kind of like kind of function notation, function relations, and we have to have unique function value, kind of like that. Let's see, is there anything more we can talk about? Monotone sequence theorem. Well, here's a proof, but that's left to interested students only. That's a bit too much. And then decimal expansion, we already talked about it. Cauchy sequence theorem, maybe. We're not going to prove it, of course. What we're going to do is just talk about it. Limit exists. So limit exists means the difference between arbitrary terms gets down to zero. So it's not absolute value of an minus an plus 1 or something like that. M and n are unrelated, except that they are both humongous. And that's pretty useful because this condition over here does not specify a candidate of L. So if we have really no idea where this sequence converges, and if we still want to prove that it converges, then you can look at the Cauchy condition. The difference between arbitrary terms, an minus an, goes down to zero. If that happens, then the series must converge. As a matter of fact, the proof of one direction is not too difficult. Prove that if the limit exists, then the Cauchy condition, this one, is satisfied, is not too difficult. It kind of goes like this. So the right hand side is limit of that, and we want to prove that absolute value is going down to zero. But you see, absolute value is zero, or just that real number is zero. Those two are equivalent, so you can throw away the absolute value. Limit of an minus an is equal to limit of, well, that if I know that a limit exists. So limit exists and an goes to a. The assumption is we know that, so we just insert minus a plus a there. And then what do we have? an minus a, this one, plus a minus an, that one. And then, didn't we just assume that limit exists and then an converges to a? Well, we assume that. And we are trying to prove this becomes 0. So what do we have? an minus a. Well, that's going to a minus a. That's 0. And a minus an, that's going to a minus a. So that's 0 too. So what do you get? This limit that we wanted all along, this one, is 0. So the conclusion, if the series converges, if the limit is known, or at least we can express it as a certain a, then the Cauchy condition is satisfied. Vice versa is very, very different story. If we have Cauchy condition, the difference between arbitrary terms go to 0, then the limit exists. That's not easy to prove actually. And the proof is, oh boy, that's really, really hard. And well, the easiest source I can think of is this one, Calculus by Michael Spivak, 4th edition, 2008, and then ISBN. Why did I use ISBN? ISBN number is given. So if you're interested, you can either purchase this one or you can get it from a library and then you can read it. This thing is called Cauchy sequence theorem or Cauchy condition. It is something related to Cauchy. You know this name Cauchy, so it may not be too difficult to find it from a thick book. Also, if you do not want to purchase a book, then you can just Google search Cauchy sequence theorem. With some trouble, you will be able to find out relatively good source and the proof if you're interested. Please be warned, that's not going to be easy. That's something you'll have to go through before you graduate as a mathematics major. To do that in 1000 level is going to be a bit too much. About 3000, well, that's appropriate. Cauchy series theorem, well, if we know the Cauchy sequence theorem, this is easy because limit as k is running from n plus 1 to n is nothing more than the difference of partial sums, an minus am, where I mean capital AN minus capital AM is nothing more than this sum minus that sum. So we have, well, n plus 1 to n. And this expression, this Cauchy series theorem, will be used in latter part of this textbook, as a matter of fact, without going through the rigorous detail, of course, because it is based upon Cauchy sequence theorem. But to a certain degree, we're going to use it. Now, how about some limit rules? We have constant rule, okay, and then this is again and this one, my goodness, this will turn out to be really, really hard. So you can read about it, but I'm not going to discuss it here. Some other limit rule, let's see, this is one of the easier ones, so maybe we can do it here. So how do we prove this limit rule? Well, we assume an converges to capital A and bn converges to capital B. So the difference between an and capital A is arbitrarily small, so we take it as less than epsilon over 2. Same goes to bn minus capital B. And then if we put those into an plus bn minus capital A plus B and algebraically manipulate, kind of like this, then we can apply triangle inequality so that absolute value of this and the absolute value of that is greater than or equal to previous quantity. And what do we have? We have this first one is less than epsilon over 2. The second one is less than epsilon over 2. Consequently, adding them up, the quantity we wanted to find out is less than epsilon. So that's the proof. That's a complete proof of it. The other limit rules are a little bit harder, but, well, with some difficulty and with some hard time and with some effort you can follow through.